All right, now let's use calculus to study some optimization problems involving real-world examples. These are some of my favorite problems because they involve a lot of critical thinking and some picture drawing where you have to really understand what's happening and kind of be creative with your solution. So let's ask ourselves this. We intend to build a rectangular fence. Well, there's a picture right there. Two of the sides opposite each other will be built from wood, costing $8 per square foot, or so, not per square foot, it's linear per foot, while the other two sides will be made of chain link costing $4 per foot, so about half as much. So because I've got two different materials, it's probably a good idea to draw your picture something like that, right? Represent the two different sides, one with dashed, one with solid. It doesn't really matter at this point which one we call chain link and which one we call wood. It will change the equation, but everything's going to make sense no matter what you pick. So let's make the wood. In fact, I'm going to do this on purpose. I'm going to make the wood this side, the $8 per foot. And I'm going to make the chain link the solid. This was at $4 per foot. Okay, so notice those aren't the values of, those don't give me the lengths of those lines. They give me the rates of those lines, right? It's or the rate of cost of those lines. All right, let's keep reading. If we wish to enclose 1,250 square feet, what should the dimensions of the fence be? Yeah, I think that's wild. We don't really know a lot about the problem, but apparently we know how to build this. Let's see. Why does it even make sense that I can ask how large this fence is going to be? Well, let's start with what we know. I want to enclose, so first we labeled our picture. We used all the information that the wood cost $8 per foot, the chain link cost $4. We've got two sides of both. The next piece of information is I want to enclose 1,250 square feet. So I want the area of this fence to be 1,250 feet square. All right, what do I know about that shape? It's rectangular. Let's give some variable names. Let's call this, this was the wood, so maybe we can call it W. This was the chain link, so maybe let's call that C. We can now write area as W times C, right? Length times width. Okay. Now, if I want to, what do I want to do? I guess it doesn't say, but let's imagine that we want to minimize cost, right? If I want to build this fence, I should want to build it with the lowest cost possible. So we need to come up with a cost equation. The cost is going to be, it's going to take me $8 per foot here, and I've got W feet there. So it's going to be 8 times W, right? For how big W is, for every W, I've got $8 there. So that's how much it cost me to build that part of the fence. I need to add 4 times whatever C is, and then I need to add another 8W, and then I need to add another 4C. So my cost, I guess I don't want to use C because C is already spoken for. It's my chain link dimension. My cost is equal to 16W total plus 8C. So I know that if I want to minimize cost, the only possible place that I can have a minimum is at a critical value. So when my derivative is 0 or does not exist. If we differentiate cost with respect to, what am I going to do? Oh, I know why I'm confused. My cost equation depends on two variables, and we don't know how to differentiate something with two variables yet. So I need to come up with a way to replace one of these variables, but I can use the fact that my area is equal to W times C. My area needs to be 1,250. Let's pick to solve that for C. So C is equal to 1,250 divided by W. That allows me to write cost is equal to 16W plus 8 times C. Okay, so cost is equal to 16W plus, what is 8 times 1250? That gives me an even 10,000. I've got 10,000 times W to the minus 1. The derivative of the cost function with respect to W is going to be 16 minus 10,000 W to the minus 2. So that's 16 minus 10,000 over W squared. All right, so this is going to give me a 0 or discontinuity. Let's talk about discontinuity first. So the only problem is I've got that non-removable discontinuity at 0, right? But I don't have to worry about that because my width can't be 0, right? Because if I have a 0 width, then I really don't have any area enclosed. All right, so when is this going to equal 0? So when is 16 going to equal 10,000 over W squared? Let's throw W squared onto the other side and divide by 16 and take the square root. All right, so let's give ourselves an approximation to this. Oh wait, I think both of these are nice squares. The square root of 10,000 is just 100. Square root of 16 is a 4. So when W is equal to 25, that's a critical value for my cost equation. It's a 0 of my first derivative. So I might have a minimum or a maximum there. I don't know at this point. So let's see. How can I show that it is in fact a maximum? Well, we could find the second derivative. The second derivative of the cost function is going to be, so working from that first derivative right there. This is going to be, so 16 differentiates to 0. The minus 2 is going to come down, become a positive 20,000. W to the minus 3. All right, now if you plugged in W is equal to 25 into this equation, it's not important what you get, it's positive. So your second derivative is positive, meaning that you are concave up, meaning that when W is equal to 25, that is indeed a minimum of your cost equation. So we have minimal cost when the W, what was W? W was the wood length. When the length of the wood part of the fence is 25. Cool. So if the width of the, or the length of the wood part of the fence is 25, and I take this equation here, if W is equal to 25, then C has to be 1250 divided by 25. That gives me 50. So my, what did we call the chain link? C. And that kind of makes sense, right? Because it was twice as expensive to build wood as it was chain link. So you should spend half of the distance or half of the length on wood that you do chain length.